Welcome to lesson 1 for chapter 3, Pure Mathematics Year 2. And this chapter is all about functions. And today we're going to look specifically at the modulus function, okay, as it's stated here. Now, you might not know what the modulus function is, but it links together with ideas that we covered in Year 1, all about straight line graphs, inequalities, graphs and transformations, and all kinds of other functions and graphs that you've plotted and are familiar with. So it also goes back to ideas way before Year 1, back to GCSE. So we're going to introduce a new idea, and you're going to find out what the modulus function actually means. This also means that there's going to be some new keywords. So things like the absolute value, we're going to use that, and the word modulus itself. Okay, so before we introduce this idea, I'd like you to have a go at the 4 warm-up questions. So please pause the video, try the 4 questions, and I'll go through them with you. Okay, and let's have a look at the solutions. So our first question, we're given a table of values of ordered pairs. Now, just to remind you what ordered pairs are, it's just another way of representing coordinates. So, for example, an ordered pair for the x value x equals -4. Well, clearly, if you put this x value into the function f, we get the value -2. So as an ordered pair, you would simply write that as -4 and -2, like that. It's just a pair of coordinates. You might have known that already. I just wanted to clarify based on the fact that this may be a term you're not familiar with. So that's all that ordered pairs are. Now, the first job we have to do is we have to write down a function, or the function f of x, in terms of x. So we're not really given any clues algebraically. We just have to deduce the function from the table of values. So you can see that specific values of x, it looks as though, and you may have spotted this, that whatever the x value is, the y value that you seem to get out of it appears to be 2 greater. And I hope you spotted that. So if you put in an input x, whatever it is, your output is just going to be x plus 2. Okay, and you just check that all the way down from the first row to the second row. So -3 plus 2 is, of course, -1, and so on and so on. So that appears to be our function. So we're going to write this function down as a function in terms of x, and it's called f of x. So the function f of x is simply going to be x plus 2. Okay, don't worry if you didn't spot that, but that was all you had to do for that first part. Now then, the function g of x. Now this is an interesting definition. Y equals g of x, so that's plotting the graph of g of x, represents the distance of each of the values of f of x from 0 on a number line. So, for example, let's take, for example, I'll draw a little number line here. So we've got maybe some x values. If I put the origin here, and I'll put the number 1 here, and maybe I'll put the number -2. Okay, so just imagine a snippet of the number lines, just zooming in. Now, if you'll notice, if we're interested in the distance of each of the values of the function from 0 on a number line, suppose your x input was 1, like we have here. Well, what is the distance of, and distance, I'm going to use that word carefully. It's hard to define distance when you have no unit of measurement, but in terms of the units, okay, or in terms of numbers themselves, how far away is the number 1 from the origin? Well, if you look at that, it's 1 unit away, isn't it? 1 unit of measurement, whatever that might be, but it's 1 away. Now, so I think that's pretty clear. You're 1 unit away if you're at 1 on the number line. Now, if you're at -2, how far away are you from 0 this time? Well, if you're at -2, you'd be 2 units away. Okay, the direction is irrelevant. I'm 2 units away if starting from -2 up to the origin, and I'm 1 unit away if I'm starting at 1 going back to the origin. So it looks as though the distance is simply the value of the number irrespective of whatever sign it is. So we can just disregard the sign. So let's fill that in. So if I have a value of -2, like I have in the middle row here, and I want to define that -2 as a distance from the origin in some units, whatever they may be, we are 2 of those units away from the origin. So I'm just going to put the number 2 there. Okay. And similarly, if I'm at -1, I am 1 unit away. And then I can just simply reproduce all the positive values. They're not going to change. So the distance of each number, I'm going to make that really clear. Let's highlight it. The distance of each of the values of f(x) from 0 on number line is simply the positive version of whatever that number is. Okay? So we've got our row for G completed, and that concludes question 1. Now, for question 2, we're going to plot our function g of x on the grid. Okay, so let's do that. So just be careful with your labeling. So we're going from -4 up to 2, so we can just use really clear, obvious labels, 1 and 2 there. So one big square is 1 unit, -1, -2, -3, and -4. Okay, and then obviously the G values, okay, are going from a minimum of 1 up to a maximum of 4. Okay, so let's just put those in. So it's -1, -2. I'll just put those in anyway. 1, 2, 3, and 4. Just squeeze that on. So let's put in our ordered pairs. So just be careful with this when you're reading off the table of values. It's the first number, of course. So the first number, when I say the first number, the number in the first row, that's your x coordinate, and the number in the third row is going to be your y coordinate for g of x. So we're going to start at -4, 2. So let's do that. -4, 2. -3, 1. Okay. -1, 1. Okay, this is interesting. 0, 2. And 2, 4. So what's going on here? It seems to change direction. And we have to plot this graph. Now, it's not actually clear what's going on. Is it a curve? Probably not, because we know the function f of x, which is what g of x is based on, it's a linear graph, isn't it? So surely this is just a linear graph. So we can see it here. We wrote it down for 1 part A, didn't we? But what's going on? Perhaps it'd be clearer if we figured out what's going on here when x is -2. Well, if we put -2 into this function, it's simply going to return the distance of whatever f of x is from the origin. Now, if we put -2 into f of x here, when x is -2, then f of -2 is simply just going to be 0. So it appears we are at the origin here. So it must deflect. And that's precisely what happens. So we have two piecewise continuous straight line graphs. So let's draw them in. So I'm going to try and use the straight line tool here. So there we go. So that's the first part. And then the second part is going to go like that. Okay, so we're going to label this as y equals g of x. So it's quite an unusual looking graph. Okay. Okay, so that concludes question 2. Okay, and a change of approach here. For question 3, we simply have to solve 2 equations. Now, you should have had quite a lot of practice with this in year 1, quite early on and at GCSE. So nominate a side where x is going to go and make the necessary changes. So I'm going to start off by adding 0.5x to both sides. Okay, so we'll start with that. And if I do that, and I'll continue with the decimal idea, we're going to have 3.5x subtract 2 is equal to 5. Okay, so I've added 0.5x to both sides. Now I can add 2 to both sides. So I'll just explain what I've done there. So I'm just adding 0.5x. Next up, we need to remove the 2 from the left-hand side. So by adding 2 to both sides, we can do that. So adding 2, we're going to have 3.5x is going to equal 7. Okay, and you'll notice if you multiply 3.5 by 2, you get the answer 7. So x is simply going to be 2. So I hope that was okay, and you can underline that if you want to. So just a bit of solving equations there. For part B, we have a very similar looking question. There's a subtle difference here. There appears to be a sign switch between these 2 terms on the right. So maybe that will be significant later. So we need to solve this. Now, the first thing to do is instead of having a negative 0.5, I've now got a positive 0.5. So I'm going to have to subtract that from both sides. So let's do that first. So if I subtract 0.5, I'm going to have 2.5x subtract 2 is going to equal negative 5. Okay, so I've subtracted 0.5x this time. Okay. Now I'm going to add 2 again. So I need to add 2 to clear the negative 2 from the left. So we're going to have 2.5x is going to equal. Now if I add 2 to negative 5, just be careful with that. It's going to give me negative 3. Okay. Now, if you don't like dividing that, minus 3 divided by 2.5, and you want to do it in your head, perhaps a good thing to do would maybe to write the 2.5 as a fraction. In fact, I'm going to do it like that, so we get a nice answer. So 2.5, that's going to simply be 5 over 2. So I'm just rewriting that. You can, of course, do it on your calculator. I don't mind, of course. It's up to you. It's going to equal negative 3. And then multiplying by 2 and dividing by 5, we get x is equal to negative 6 over 5. And if you want to put that in decimal, okay, that's obviously going to be negative 1.2. All right, so we've solved the 2 equations. We get 2 completely different answers from that sign switch on the right-hand side. And moving on to question 4, we have an inequality to solve. At first glance, it looks as though we're going to have to break these brackets open on both sides. So let's do that. So just break open the brackets. So we're going to have 5 subtract 10x is greater than or equal to, and multiply through by 2. So 2 subtract 6x. Okay, multiplying everything by 2 on the right and everything by 5 on the left. Once again, we need to nominate a side to collect the x's. So I think a good idea would be to put the x's on this side, because if I add 10x to both sides, I'll get a nice positive x. Okay, so I'm going to add 10x to both sides. So I'm going to show you that step here now. Plus 10x. And so it's like a mezzanine step or a sub step, if you like. So the next full step would look like this. So 5 would be greater than or equal to 2. And if I'm at negative 6 and I add 10x, I'm going to have plus 4x like that. Okay. And now I'm going to subtract 2 from both sides. So once again, subtracting 2 will clear the 2 from the right-hand side. So that's going to give me 3 greater than or equal to 4x. Okay, and dividing through by 4, we get x is less than or equal to 3/4. Okay, now that's one approach. An alternative, you could have gone a different route here. Now I'm just going to explain why this is important. If we just do a little side step here, I'm just going to talk about an alternative approach. Suppose we decide to add 6x to both sides instead, okay, to clear the x's from the right hand side. We would get 5. Now adding 6x would obviously give me negative 4x on the left, which is greater than or equal to 2. Okay, by adding 6x instead. So I'm just making note of what I've done there. So I've added 6x. Next up, I would like to subtract 5 from both sides to make sure I've got the x term all by itself on the left. Now, if I do that, I'm going to get negative 4x is greater than or equal to subtract 5, which is negative 3. Okay. Now, at this point, you'll think, okay, I just have to divide through by negative 4. And if I do that, and don't write this step down, this is just for your reference. If I just divide through by negative 4, I get, obviously the 2 negatives will cancel out here and here. So I get 3/4, but you'll notice there's a problem because in the first way I did this, I calculated that x was less than or equal to 3/4. Here I've got the opposite. I've got, or not quite the opposite, but I've got x is greater than or equal to 3/4. So something's gone wrong. And you need to be really cognizant of this step. It's all about this negative division that I did in that very last step. So getting from there to there, I've made an error. Okay, so this is clearly not true. So I need to do something else here. So the trick, and it is a trick at first glance, the trick is to switch the inequality around. If you're dividing through by a negative, which is what I've done here, I've divided through by negative 4, I'm forced by convention to switch the inequality round. So the inequality has to switch round and I get 3/4. Now you'll probably think, is that a bit of a fudge? Like why do that? Why should I know this? Well, and obviously, sorry, you're going to divide through by negative 4 on this side as well. Otherwise it's not an equation. So why do you have to do the switch? I'm just going to tell you very quickly. Well, because it's an inequality, suppose you write down a true statement. So just any old true statement, such as 2 is strictly less than 3. Now, everybody would agree that is a true statement. 2 is definitely strictly less than 3. But what would happen if I put negative 2 and negative 3? Okay, is this still a true statement? Well, obviously not. Okay, so obviously there's a problem and the inequality has to switch round in order to make it a true statement. So that has to switch round and we're forced to write it like this. So we would have negative 2 would have to be greater than negative 3, simply because I've multiplied both sides by negative 1, or you could think of it as I've divided both sides by negative 1. It does the same thing. So any kind of multiplication or division by negative numbers, the inequality has to switch around. Okay, right. So that concludes the warm-up. Okay, so now let's take a look at the modulus function. What actually is it? So it's got two names essentially. So the modulus or absolute value, you can use either of those interchangeably, of a number x. So let's assume this is a real number x, and you write it as the number with two bars, one on either side. Okay, that denotes the modulus or absolute value, and this is the distance of the number from 0. More simply, I think it's the non-negative value of x. So it's x with any negative sign stripped away. And the simplest way to define it is with an example, I suppose. So if we look at, for example, the number 5, the modulus of 5, so that's 5 with the bar around it, is just equal 5, because 5 is obviously a positive number. Similarly, if I take the modulus of negative 5, then applying the modulus removes the negative sign. And it's defined as a piecewise function. And you've seen the piecewise function in the warm-up because we saw a graph that deviates, it changes direction. It's a combination of two different straight line graphs. And you can see that here because we have two conditions. If x is greater than 0, the modulus function will just simply return the value of x with no changes. However, if x is less than 0, as you can see here, the modulus function will change its sign by multiplying it by -1. And I can demonstrate that just very quickly here. So if we take, for example, the number 2, 2 is clearly greater than or equal to 0. That is a true statement. All right. So therefore, the modulus of 2, because that's a positive number, that is concurrent with the top row, we just have to return the number 2, don't we? Okay, it's a positive number according to this function. If I take the number -3, -3 is strictly less than 0. So that fits in with the second row of the modulus function. And the function tells me that if I want to find the modulus of -3, I have to multiply the -3 by -1. So it's equal to minus -3, like that. I have to multiply the -3 by a -1. The two negatives make a positive. So by doing that, you remove the negative sign. So this is going to equal 3. Okay, I hope that's clear. And then also you can do the same thing with functions. So the modulus of a function is defined in exactly the same way. You simply replace the x from the modulus of x with f of x. Okay, and it behaves in the same way. Now, we're going to have a look at some worked examples, 3 very quick ones, just to get you used to the idea of the modulus and how it fits in with the work you've already done on functions. So for the first one, we have to find f of 5, and we have a modulus function defined here. So we substitute the number 5 into that function. If you like, just pause the video and have a go yourself. Okay, so for A, f of 5, and we're going to do this very carefully because this is a new idea. It's going to be the modulus of 2 multiplied by 5, obviously, because I've got to substitute 5 in. For x, okay, then I have to subtract 3, close the modulus sign, and then add 1. Okay, so as you would any other function, we're going to use BIDMAS here. We're going to evaluate what this is inside the modulus first before we can apply the modulus function. So if we evaluate that, that's going to be the modulus of 2 multiplied by 5, which is 10, subtract 3, which is 7. So I'm just going to replace all that with 7. Let's close the modulus and add 1. Okay, so now we apply the modulus function to 7. Well, obviously 7 is a positive number, so it doesn't change. So this is simply equal to 7 plus 1, which is 8. All right, I hope that makes sense. Okay, so that's f of 5. For part B, f of -2. So perhaps we'll have something different going on here. So f of -2, we're going to substitute in -2 for x. That's 2 multiplied by -2 this time. And then subtract 3. Close the modulus, and then we're going to add 1 outside of the modulus. So this is going to equal the modulus. Now, 2 lots of -2 is, of course, -4. Subtract 3 is -7. Okay. So the modulus is going to come into play here. If I take the modulus, of course, of -7, because it's a negative number, that negative sign will be removed. So that's just going to become 7. Okay, so this is going to equal 7 plus 1, which is, again, 8. So you'll notice there's this, that's the symmetry of the modulus. It's that V shape that we saw in the warm-up. You get the symmetry about that inverted apex at the bottom. Okay, so it seems we have the symmetry at 5 and -2 also for this function. And then for part C, we're going to find f of 1. So we put 1 in. Let's see what happens here. So this is going to be the modulus of 2 multiplied by 1. And then once again, we're going to subtract 3. Close the modulus and add 1. Okay, so this is going to be the modulus of -1. Okay, so 2 subtract 3. Add 1. Now, again, applying the modulus function to -1 is going to return 1. So it's going to give me 1 plus 1 here, which is, of course, 2. So that's how it works. So it's a function, like any other function, that removes any negativity from your number. So next, we're going to have a look at how to sketch the modulus function. Now, for sketching modulus functions, there's 2 approaches that I've isolated. And we have approach A, which we're going to look at first, and approach B. For this example, just to cover all bases here, we're going to look at the modulus of 2x plus 1. Okay, so it's a straight line graph, but the modulus function is applied to it. So how would we sketch this? Well, there's 2 steps behind this type of sketch. The first step is to remove the modulus sign. So imagine that the modulus sign isn't there, and you just have to sketch the graph of 2x plus 1. So that's what we're going to do. Excuse me, that's what we're going to do first. Okay, so I've just added the axes to the sketch. So we're ready to sketch the graph, and it is just a sketch, but we do need to be reasonably careful with this. So from your sketching straight line graphs that you did probably at key stage 3, we have a gradient of 2, and we have a y-intercept of +1. So I'm going to just indicate that y-intercept first of all on the sketch. So just be reasonably realistic. So I'm going to put it about there, and it's got a fairly steep gradient. So I'll put that straight line on there now as well. So let's make sure it passes through that point that I've just indicated. So it's going to be reasonably steep, maybe something like that. And it's also got an x-intercept that we need to think about. So what would the x-intercept be? Well, we can do a little bit of rough work at the side. So the x-intercept occurs when y is 0, of course. And when y is 0, we have 2x plus 1 equals 0. And just to rearrange that, we get x would be -1/2. Okay, so that's your x-intercept. So just indicate that on your graph as well. So -1/2. So let's put that on there. So just run out of space because my origin symbol was there, but you can see where it is, and that's at the point 1. Okay, I'm not writing the coordinates because we're going to be doing something else in a moment. So that's the graph y equals 2x plus 1. I'm just going to label that because we've sketched it, as is customary, what you should do. Okay, so there shouldn't be any alarm bells with that. It's just a normal sketch of a straight line. But for step 2 here, we're told that we have to reflect the section of the graph that lies below the x-axis in the x-axis. So the section of the graph that lies below the x-axis is obviously this part here. This is below the x-axis here. And the instruction tells me I have to perform a reflection in the x-axis. Now, obviously, the x-axis is the horizontal line. So I'm just going to go over that. So this is now my mirror line. I'm just going to go over it in red. That's now my mirror line. So I reflect that negative part in that mirror line. What will happen? Well, let's see. So I'm going to put the mirror image. I'll try and do a mirror image if I can. So it's going to go something like that. All right. So that blue line is a response to that mirror image. Okay. So this means if I just go over my green line here, my blue graph is now the modulus of 2x plus 1. So we have that distinct V shape. So let's just make a note of that. So y is equal to the modulus of 2x plus 1. Okay, so as you are aware, because it's a function, any negative part of the function, so in other words, any part of the function that is lying below the x-axis where y values are negative, is instantly made positive by the modulus function. So it's a reflection. That's why you get that V shape. And you'll notice, of course, the modulus function retains the features of the y-intercept at 1 and the x-intercept at -1/2. Okay, but the x-intercept is now the point of reflection. All right, so that's the first approach. So sketching the graph without the modulus and then applying the modulus by performing a reflection. Okay, so the approach B is completely different. We're going to start off with a parent function. So the parent function is the standard modulus function. So when we're talking about straight lines at least, so it's the modulus of x. Now, it's essentially the graph y equals x, but modulus. And it's very simple to draw, as you'll be aware. It's just going to be the graph y equals x for positive x values. That's a diagonal line there. Okay, and for all negative values of x, it's going to be the graph y equals -x. So another diagonal line in that direction. So that's roughly what the modulus of x will look like. So we'll just label that. Okay, so that's going to be my parent function. So I'm going to perform some transformations. Now, if you have one eye on what's going on here, and you might want to do this as maybe 3 separate sketches, it's completely up to you. This is our target. We're aiming to get the modulus of 2x plus 1. Okay, so that's our aim. So how are we going to do that? Well, we need to know something about the order of transformations, don't we? So I've given you the order of transformations here. So remember, we're starting with the graph y equals the modulus of x, which we have on the board already. And the first thing we have to do is perform any horizontal translations, right? So horizontal translations that would be a number added or subtracted inside the function. Do we have that? Well, yes, we do. It's here. Okay, it's the +1. So our first transformation is going to take us to the graph. Let's undo that. Sorry. It's going to take us to the graph y is equal to the modulus of x +1. Okay, and that might be counterintuitive. You might think that we should be doubling the x value first by multiplying by 2, but that's not how you do it. You have to apply the transformations in this order. So we're going to add 1 inside the function. And what is the effect of that? Well, this is going to cause a shift to the left by 1 unit. Okay? All right. So in other words, by the vector -1, 0. So if we do that, we'll just put that on the diagram. So I'll stick to this pink color. We're going to shift everything one unit to the left. So the diagonal line is going to be parallel to the line y equals x, and this part will be parallel to the line y equals -x. So that's what we've got so far. So that's going to be the graph y equals the modulus of x +1. Okay, so we have one more transformation to perform, and it's worth at this point just thinking about where this graph is intersecting both the x and the y axes. So we can see clearly we have 2 points of interest here. Now, if you substitute in x equals 0, that's obviously going to give you a y-intercept of 1. Okay, and if you set y equal to 0, then you can just solve the equation x + 1 = 0, which is of course going to be -1. Okay, but if you want to do that as an aside, you can do. Now then, the next transformation we're going to perform is the horizontal stretch. Now, there is a horizontal stretch. There might not be, but in this instance there is. So the horizontal stretch, this is where we multiply the x variable by 2. So what's that going to do? Well, that's going to give us the function that we want. So this will give us y equals the modulus of 2x + 1. If we do that, and if we're multiplying by 2 inside the function, then remember it's the inside opposite rule. So essentially what's going to happen is that we're going to multiply the x coordinates scale factor of half. Okay, so in the x direction. So nothing will happen to the y values at all, but the x values are all going to be halved. And what's the consequence of that? Well, if we look at our diagram, this -1 here is an x value, isn't it? It's where the apex is, the inverted apex. That's going to have to be multiplied by 1/2, okay? Which is going to bring my apex halfway between 0 and 1. But because the y values do not change, you'll notice what seems to happen here. So I'm going to do this in blue. It's still going to pass through the point the point 0, 1 on the y-axis. So this is going to create a steeper graph like that. Okay, so it's still going to pass through 0, 1. So it has that stretch squeeze effect, doesn't it? So it's going to double the gradient essentially. And then the same thing is going to happen for the negative branch, as I call it. Okay, so let's label that. So this is going to be the final sketch, which is the modulus of 2x + 1. And as I said, you might have wanted to do that as 3 separate sketches, perhaps starting with the parent function. So just to highlight the one we're looking at, this is your final answer. So it's going to intersect the x-axis right here. I'm just going to label that at -1/2, as we saw previously. and it's going to intersect the y-axis at 1. All right, so that's approach B. So it's a case of you decide now which approach you prefer, and you can carry that forward well as we do some more examples. Okay, and just for the last little bit on this page, we're going to look at sketching a function which on the face of it looks rather complicated, but you can see that it contains the modulus of 2x plus 1, which we've spent the last few minutes working on. And the only difference is that we have this -1 on the outside of the function. So if we continue applying the order of transformations, to get the modulus of 2x plus 1, which I've sketched again on the axis provided, we've now got to add yet another transformation. And the green transformation that I've just highlighted is, as I've already said, outside of the function. So this is outside of that modulus function. Now, when it's outside of the function, and I'm using that word outside loosely, this is going to be some kind of transformation in the y direction. We just got to decide which. Now, it's not a multiplication outside of the function. So I'm not multiplying my modulus by some constant. So it's not going to be a vertical stretch. Okay. What this is, it's a vertical translation, and that's the final transformation that you perform. So the vertical translation means that I'm going to take my modulus of 2x plus 1. I'm going to take that graph, okay, and I'm going to translate it by the vector 0, -1, okay? It's exactly what you'd expect. So the y values are going to have 1 subtracted from them. So what happens to the diagram? Well, you'll notice, of course, that the y-intercept is currently at 1. So all the y values are going to have 1 subtracted from them, which lowers the graph by 1 unit. So if we're going to draw our final graph, okay, which I'll do this in pink. So it's going to be exactly the same shape, except it's going to be lowered. I've not drawn that very well. Let me just move that slightly. So there we go. Okay, and it should be parallel. So it's now going to pass through the origin because I've subtracted 1 from all the y values. So that's dropped down by 1 unit as required. And we're also going to do the same thing to this negative branch here, as I call it. So it's going to look like that. Okay, so you might be thinking, well, hang on a minute. It's a modulus graph. Why is it dropped below the x-axis? I thought that modulus graphs are always positive. Okay, well, the answer is, of course, not always. Okay, it actually behaves in a very similar way to a quadratic. Okay, in the way that squaring makes things positive, so does the modulus. And it's basically a straight line version of a quadratic. Okay, and you can apply moduluses to quadratics as well. So what's going to happen here? Well, we still have that minimum point is still when x is -1/2, but now that point has been shifted down by 1. So we're now at the point -1/2, -1, which is this point here. And there are 2 roots as well where the graph crosses the x-axis. So we'll talk more about that later. But for now, let's see if we can just label what these roots would be. So the first one is obviously the origin. Okay, and by symmetry, if we just look at the distance from one side of that apex to the other, so that's ½ a unit. So we go another ½ a unit in that direction. So that's going to be at -1. Okay, so that's going to be the point -1 there. All right, and we'll label that graph as required. So this is y is equal to the modulus of 2x plus 1, but it's been shifted down by 1, so we put a -1 on the end. Okay, so I hope that's clear. So let's move on and do some more examples. All right, so let's have a look at some worked examples. Now, for the first one, I've just sketched the axes for you already, ready for the diagram. And I've also just written out the definition of the modulus of a function. And the reason for that is there are usually, or it's quite common to have misconceptions about where the changeover takes place. So a function that has the modulus applied to it is always positive. Okay, that's the first thing. Okay, if the function is within the modulus itself and there's no other constants added or or anything like that outside of the function. So it's just the function with a modulus on the outside. Now, if we consider that, if the function is, of course, positive, then, i.e., the function is above the x-axis, which is denoted by that. If f of x is greater than or equal to 0, i.e., above the x-axis, you just take the function as it is at face value. However, if the function is negative, it has to be reflected. Okay, it's an instantaneous reflection. So those negative values, which you can see very clearly from this, because they are negative values if they are strictly less than 0, they have to be made positive because the modulus dictates that all the values are positive. So we have to multiply our f of x by -1 to create those positive values. Now, in the context of this question, we're looking at the modulus of 2x subtract 1. And we'll see this materialize on the sketch in a moment. If I take the modulus of 2x subtract 1, this is equal to this piecewise function. So it's either going to behave like 2x subtract 1 if the function itself, 2x subtract 1, is greater than or equal to 0. Okay? Secondly, it's going to be negative, the negative version of this function. So the negation of the whole thing if the function itself, 2x subtract 1, is less than 0. Okay? So that's how it behaves. Now, you can also see that we have some inequalities we can actually solve here. So we have an inequality here that we can solve. Now, if we rearrange and solve for x, you can see that this is going to give us x must be greater than or equal to 1/2. Okay, and in this situation, underneath, x would be less than 1/2, and between them, they will cover the entire real line. So there are two branches to this function. There is what I call the positive branch, which is the 2x subtract 1 here, and the negative branch, which is the same function but multiplied by a -1. And you're going to see those two branches in action. And they are valid for the positive branch when x is greater than or equal to 1/2, and the negative branch is valid when x is strictly less than 1/2. Okay, so let's use approach A, and let's see if we can solve this equation. So for approach A, we're going to sketch, first of all, the graph of y equals 2x subtract 1. Okay, so let's do that. So we're going to sketch y equals 2x subtract 1 first, and then we're going to apply the modulus function. So I'm going to do this in green. Let's do that. So it's got a y-intercept at -1, and it's got a gradient of 2. So something like that may do, hopefully, something like that. Let's label it. So this is going to equal, so y is equal to 2x subtract 1. And where are the x and y intercepts? Well, the y-intercept is the constant on the end. And if you set y equal to 0, let's do a little sum here. That means 2x subtract 1 equals 0. So x is equal to 1/2. All right. So that point must be at 1/2, 0. Now we need to get our modulus. Now the modulus, remember, we reflect this negative branch, okay, so I shouldn't say that. We reflect the negative part here in the x-axis. So let's do that. So I'll do this in blue now. So my y-intercept at -1 is going to be reflected, and it's now going to be a y-intercept at 1. Okay, and then we keep the positive branch there. So we've now got a V-shaped graph. What you can do now is you can just erase the green line. We don't need that anymore. And we can just label this as the modulus of 2x subtract 1. And look what we, and I'll just, that's a bit of a gap there. And you can see what we said earlier has happened. We have a switch over, and that's the y-intercept at 1. We have a switch over when x equals 1/2. So the positive part of the graph is valid when x is greater than or equal to 1/2. So that's the equation of the positive branch. So I can just label that. So this branch is y is equal to 2x subtract 1. And the negative branch, when x is less than 1/2, is the negation of that, as you can see there. So the negative branch, so this is going to be as follows. So it's going to be y is equal to the negation of that. So it's minus, just putting that in red, 2x minus 1. And that's the negative branch. Okay. In other words, this part of the graph. Okay. All right. Now we have to solve the equation when this graph is equal to 5. So we're also going to sketch the graph y equals 5 on here. So, and y equals 5. So just for sake of accuracy, I'm just going to move this label a little bit. And we'll put the line y equals 5 in pink across. So it's going to be maybe somewhere across here like that. It's a horizontal line, isn't it? So that's going to be the line y is equal to 5. Okay. And I'll just relabel my modulus graph again. Y is equal to the modulus of 2x subtract 1. Okay. Now, if you look at the diagram, we seem to have 2 points of intersection. We have points of intersection here and here. So if we read off those values of x, that will be, or that will give us the solutions to the equation. Okay, so we need to figure out what those values are, and we can do this algebraically. So to do this algebraically, we just need to figure out what the equations are we need to solve here. So we're going to solve, first of all. Now, if you look at the, I should just indicate this point here. What lines are intersecting? Well, it's the negative branch intersecting with y equals 5. So we're going to have to solve the equation minus 2x minus 1, which is the equation of the negative branch, is equal to 5. Okay. And why don't I label that? So this is, we'll call this point A, and we'll call this point B. And this will give us the x coordinate of A. Also, we have another equation to solve. So we have the positive branch of y equals the modulus of 2x subtract 1, which is just 2x subtract 1, isn't it? It's just the same. And when is that equal to 5? Okay, and that will give us the x coordinate of the point B. Okay, so we solve them separately. So first of all, I've got to multiply my bracket by minus 1, so that's going to be minus 2x plus 1 is equal to 5. If I subtract 1, we get negative 2x is equal to 4. Therefore, x is equal to negative 2. Does that look like a sensible answer? Well, I would have thought so. If we just use the sketch here, if I read off from there, looks like it's going to be a negative number. So that looks pretty convincing. And for part B, we solve that equation. So we have 2x, add 1 to both sides, is equal to 6. So x must be equal to 3. Okay, and does that look reasonable? Well, it all depends on how good your sketch is, doesn't it, really? So that's about there. And it's not too bad. You can see relative to the y-axis, it's slightly further on, isn't it? So yeah, we've got our values. So this is at the point -2, and this is the point 3. And we have the solutions to our modulus equation. Now, for worked example 2, we have just sort of moving up a notch here. We've got the modulus of x subtract 3 is equal to a linear equation this time. So it's the linear equation of what we've just been looking at, in fact. So if I plot the linear equation first, so we'll just label this 1 and we'll label this 2. So for part 1, I'm just going to simply sketch 2x subtract 1. So we're going to sketch this first of all. Okay, so y is equal to 2x subtract 1, which we know what that looks like because we've dealt with it already. So I'll do it in the same way. So y-intercept at -1 and a gradient of 2. And notice this is not modulus, so it's just going to relatively steep, so something like that. Okay, and we'll just label that and make sure we've got the x and y intercepts labeled as well. So this is y is equal to 2x subtract 1. And we remembered, hopefully from previously, what the x-intercept is. That is at 1/2, and the y-intercept is at -1, as you can tell from the equation. So that's the first thing. So considering the right-hand side first of all. So next thing, we're going to have a look at x subtract 3 in the modulus. So we're now going to have a look at sketching y is equal to the modulus of x subtract 3. Okay, on the same diagram. Now, using approach A, as I did previously, we simply have to sketch the graph of x subtract 3 and then reflect it in the x-axis for any parts of the graph that drop below the x-axis. So let's have a look at that. Well, we've got a y-intercept at -3, and it's not a particularly steep gradient. It's a gradient of 1, isn't it? So I can't have it as steep as what I've got here with 2x subtract 1. So I'll do this one in pink. So at the moment, the graph of, in fact, no, I'll do this in light blue. So the graph of x subtract 3, it's going to cut at -3. So I'll put it somewhere around there, and it's got to have a less steep gradient. It's a diagonal line essentially, isn't it? So something like that will probably do. Okay, so I'll just label that what I've just done. So this is y is equal to x subtract 3, not modulus. And where does this cross the x-axis? In fact, let me just make that a bit more realistic. I'm just going to have another go at that. So maybe something a bit more like that would be better. Okay. Where does it cross the x-axis? Well, if you set y equal to 0, it's pretty clear you're going to have an x-intercept at 3. And of course, you can see the y-intercept is at -3, okay, for this graph. But we have to take the modulus, okay? So any negative part has to be reflected. And you can see there's lots of negative parts of the graph. In fact, it's an infinite stretch, isn't it, below the x-axis in that direction. So all that has to be reflected. So we'll do that now. And once again, I'll do this in blue. So we'll reflect the graph. So it's now going to cut at +3 instead. Okay, and I'm just going to go over this. So we have a dark blue graph now. And this is the graph of y is equal to the modulus of x subtract 3. Okay, now you can use an eraser for this. So we're just going to get rid of that old graph because we don't need it anymore. Okay, we used it as a guide to draw our modulus graph. And notice we keep the x-intercept right here. We keep that. That's that inverted apex, but we have a new y-intercept, which is reflected from -3 down here to +3. So we're going to indicate that on there. Okay, so that completes the sketching. And because we've been reasonably accurate with the gradients as well, we can see hopefully that there is one point of intersection only, because the graphs are going to diverge. This is a, excuse me, let's do that again. The modulus graph here, that's obviously just x. It's got a gradient of 1. This has a gradient of 2. They are diverging, aren't they? Okay, so it's the point of intersection we're now interested in that we've got to figure out what the coordinates of this are, or the x coordinates at the very least. So by my diagram here, I can tell it's going to be somewhere between 1/2 and 3. So how do we do this? Well, we have to consider which branches are intersecting. So what we're going to be solving. Well, if we look at the green line, we have no choice. That's the equation y equals 2x subtract 1. So I've got to use that. But what is it intersecting with? Well, it's intersecting with the negative branch of my modulus graph. So it's intersecting with this branch here. Now, as you know, as we've talked about already, these modulus graphs have 2 equations. They're piecewise continuous and they switch over for all x values that are positive. So, for example, this equation is x subtract 3, okay, for that positive branch. And this equation here is the negation of that. So it's y is equal to minus x subtract 3, like that. Okay, it's the negation of the function. Okay, and this is valid, and this is where we've got to be careful. So this is valid when x is less than 3. Okay, as you can see from the diagram. And this is valid when x is greater than or equal to 3. Okay, so just worth considering there. So we set our equation 2x subtract 1 equal to minus x subtract 3. Okay, it's the negative branch of that line. So now we've done all that work, this is all we have to do now is to solve this. So next step, we're going to expand the bracket on the right hand side. So therefore 2x subtract 1 is going to equal negative x plus 3. Now I'd quite like to clear that negative x on the right hand side here. So I'm going to add x to both sides. So this is going to give me 3x subtract 1 is equal to 3. Okay, adding 1, we have 3x is equal to 4. So x is equal to 4 over 3, which does indeed sit between, okay, this value does sit somewhere between 1/2 and 3. So we seem to have solved our equation. And for our last example, we're going to consider 2 graphs again. So I won't do the numbering. I think we're getting used to this. We're going to consider the graph of y equals 2x and also the graph of the modulus of 3x subtract 2 as equal to y. So let's just make a note of that. So we're going to sketch, first of all, y is equal to 2x and y is equal to the modulus of 3x subtract 2. And that will take a little bit more work. So we'll sketch the graph of y equals 2x first on the diagram. So the y-intercept is, of course, 0, isn't it? It's the origin, and it's got a gradient of 2. And when you're sketching this, just bear in mind the two gradients that we're looking at. We've got a gradient of 2 and we've got a gradient of 3 in this one. So just consider the steepness of the lines. So we have a reasonable looking sketch. So I'm going to sketch this in green again. So we'll have a nice straight line going through the origin, gradient 2. So let's do that. So something like this. In fact, I think that's probably too steep. So I'm just going to move that a little bit to there. All right. Okay, so we'll call that one y equals 2x. Okay, with no modulus. And now we have to consider the modulus graph. Now, we sketch the graph of what's inside the modulus first using approach A. And if we do that, so I'll do that in light blue, 3x subtract 2, well, that's got a y-intercept of -2 and a steep gradient of 3. So if I do that, it's got to be steeper than what I've got already, and it's got to cut somewhere below the x-axis. So something like that might do quite nicely. Maybe it doesn't need to be quite as steep as that, so maybe about there. Okay, so we'll call that equation y is equal to 3x subtract 2, and some of that will be erased later. So where does this cross the x-axis? Well, we'll just do a little calculation. If you set y equal to 0, then 3x subtract 2 is equal to 0. So obviously x is going to be 2/3. All right, which looks reasonable from the sketch. So that's going to be at the point 2/3. And the y-intercept is clearly -2, because we can see that from the gradient. Okay. Now, to create the modulus, we reflect all the negative parts of the graph in the x-axis. Okay, so that's going to give us a function. Let's do it in orange this time. Why not? So the negative, no, let's not do that. That's what I'm using. Let's do it in purple. So the negative part of the graph, I reflect it. My y-intercept is now going to be mirrored to the point 2, and it's going to be symmetrical about the equation x is equal to 2/3. Okay, so that's my new y-intercept now at 2, and we retain the 2/3, which is now the inverted apex. So what I can do now, I'll just go over my original graph here, and then I can delete the line y equals 3x subtract 2. So you can do that with an eraser as well. So we'll delete that, and we'll relabel it as follows. So this is the graph of y is equal to the modulus of 3x subtract 2. Now, I just want to spend a bit of time talking about why the two branches switch over at 2/3. So if you remember from the definition of the modulus, if we take the modulus of some function f of x, it has two branches. F of x without the modulus, if the function itself is greater than or equal to 0, because that specifies that the function is above the x-axis, and negative f of x if f of x is less than 0. Now, in this instance, the function that we're talking about is 3x subtract 2. So if we solve the inequality, when is the function 3x subtract 2 greater than or equal to 0? Well, that is when, of course, x is greater than or equal to 2/3. Okay, which you can see clearly from the diagram. It's when the graph is above the x-axis, and it's true when all the x values are greater than or equal to 2/3. Okay, and similarly, if I apply the same rationale for the negative branch, it's when 3x subtract 2 is less than 0. So that's when x is strictly less than 2/3. Okay, so that covers the entire real line, doesn't it? Okay, so I just thought I'd mention that. Okay, now if you look at what we've got on our diagram, we seem to have 2 points of intersection. We seem to have a point here and a point here. So we have an intersection with both the positive and the negative branch of our modulus function. So I'm just going to indicate the equation of that negative branch on the diagram. So remember, of course, I'm just going to highlight it as well, the negative branch. This part here, you simply negate the equation of the straight line. So this has an equation, y is equal to minus, and we'll put everything else in. So minus 3x subtract 2. Okay, it's not a reciprocal. I must stress that. So negative 3 as a gradient and 3 are not reciprocals of each other. Okay, that would mean that the two modulus branches were intersecting at 90 degrees. Sometimes they'll do that, but most of the time they won't. All right, so we have to solve two equations. So we can see that the negative branch is intersecting the line y equals 2x right here. Okay, and the positive branch is also intersecting the line y equals 2x there. So let's solve those two equations. So we're going to solve, and I know it's an inequality, but we'll just consider this as an equation first of all. So we're going to solve the equation 3x subtract 2 is equal to 2x. And for the negative branch, minus 3x subtract 2 is also equal to 2x. Okay. First one, just subtract 2x from both sides and add 2. So we're going to get x is equal to 2. I hope that's okay. So just subtracting 2x from both sides will give us x subtract 2 and then add 2. And on for the second equation, I'm just going to multiply through by minus 1. So that's going to be minus 3x plus 2 is equal to 2x. And I'm going to add 3x to both sides now. So if I do that, I'm going to get 5x there. So x is going to equal 2/5. So how does this correspond to our diagram? Well, you can see by observation, or inspection, I should say. Of course, you can see by observation. That's what that's what it is. Those two values, this must correspond to the 2/5 because it's between 0 and 2/3 where that apex is, and this point here must be at the point 2. Okay, so we've solved the equation, but we haven't answered the question. It's an inequality. Right. So how do we solve this inequality? We're interested in the modulus graph being greater than, strictly greater than 2x. So what I'm going to do, now we've got all those values, I'm just going to remove some of this detail from our diagrams here because we don't need all this. And we need to have a nice, clear idea of what's going on. So if you look at the modulus graph, when is it greater than 2x? Well, we could shade in the region, couldn't we? It's greater than 2x here because that modulus line is above the green line, and it's also greater than y equals 2x there because that's also where the modulus line is above the line y equals 2x. So how do we answer the question? Well, we just state the two regions. So clearly, or I say clearly, I hope it's clear, the modulus graph, so the modulus of 3x subtract 2 is greater than 2x when x is strictly less than 2/5, okay, which corresponds to this part here, where the modulus line is above the green line for 2x, and when x is greater than 2. Okay, which again corresponds to this part where the modulus graph is above the line y equals 2x. Now, let's just say for the sake of argument, if you had the opposite question, when is the modulus graph strictly less than the line y equals 2x, you'd have the opposite region. You would be interested in this region here, okay, where the modulus graph is below, and that would be between 2/5 and 2, okay, not including either of them. So this is why sketching the graphs is really important. So the final answer is 2 branches. So x is strictly less than 2/5 and x is greater than 2. If you're not sure whether you've got the right answer, pick an x value that is strictly less than 2/5, something easy like 0, and pick an x value that is greater than 2, put them into the inequality and check that they work. Okay, so that concludes the lesson on the modulus function.